So in the class today, we're going to start the first of three classes about the web ontology language. So the idea of the web ontology language is to extend what we previously saw with RDFS with the ability to define more types of axioms and definitions. So the last time we focused, we started to speak about this layer of the semantic web. So we saw with RDFS that we can principally define four main aspects: subclasses, subproperties, domains, and ranges. Today's topic, we're going to start to talk about a second standard for defining logic, or in fact ontologies of the semantic web, which will actually allow us to define these rules here, which we couldn't do in RDFS. B capital of A implies A part of B. We didn't see a way to do that yet. And A part of B, B part of C implies A part of C, and a lot more. So if RDFS is sort of the tip of the iceberg, OWL is considerably more deep. So it allows us to express a lot more things than RDFS. And that in itself comes with some issues that we'll also discuss. So to give an example of why it might be interesting to have more expressive reasoning, something more than RDFS, we'd like to model more complex domains, for example, in biology or law or astronomy or whatever. I guess in the domain of biology, this is what's known as a zebroid. It's a cross between a horse and a zebra. So if we think about a zebroid and we were to have this graph here, which tells us that Zach is a zebroid, and Zach's sire or father is Marty, and Zach's dam or Zach's mother is Leah. And here we have Sia. Sia has the same sire and the same dam. What could we intuitively conclude about Sia here? Any suggestions?
That she's a zebroid?
Yep, that Sia is a zebroid, right? So it's an interesting example because if we think about how we figure this out, okay, this is kind of maybe something that we would figure out in a very intuitive way, maybe. But why? How do we figure this out, right? What kind of reasoning do we apply for this? So here I would say, okay, maybe one could argue that it's inductive, that somehow people learn from examples, lots and lots of examples that this is the case. But I would tend to argue that this is probably deductive because we haven't seen zebroids yet, and we probably haven't really, inductively learned from all those examples. Maybe one could argue from other species, but I think this is mostly a deductive thing, that we realize that a zebroid is someone who has a horse, one parent a horse, another is a zebra, and that this must be the case for Zia, therefore Zia is a zebroid. So how could we capture such semantics or such inference in the case of the web, for example? So what assumptions do we make to conclude that Zia is a zebroid? So if we think about what we're thinking, or what we've stated, we could say that, okay, if X has the same sire and dam as Y, and Y is a zebroid, then X is a zebroid. We could apply this sort of rule here. But I don't think that intuitively that this is what we are actually applying, right? This rule is very specific to this example. It's not like we ever learned this rule here, right? That if X has dam Z1 and X has sire Z2 and Y dam Z1 and Y sire Z2 and Y type zebroid implies X type zebroid. I don't think that's how we're remembering this. This rule would be very specific to this example. And we could define lots and lots of different types of rules of the same form like this. So it's not a very general thing. However, if we maybe define some more general assumptions That would seem to be more along the lines of how we come to this sort of conclusion. And that could also be applied to classify or to find other instances of Zebroid in a much more general way than just this one case. So by general assumptions, I mean things like sire is a subproperty of parent, dam is a subproperty of parent, a Zebroid has exactly one parent, a zebra. A Zebroid has exactly one parent, not zebra, and an equine. An equine being a horse, a donkey, an ass, a mule, a zebra, sort of horse-like creatures. So Zebroid, I'm not sure if it has to be, I think it's a Zorse if it's a horse and a zebra, but okay. It's actually the more specific definition is it's a zebra and a non-zebra equine. So it could also be a zebra and a donkey, for example. A zebroid has a subclass of equine. So a zebroid is a type of equine, horse-like animal. An equine has exactly two parents. We could even define this more generally and say that an animal has exactly two, biological parents. And two things cannot be related by sire and dam at the same time. So you can't have the same, a horse can't have the same father and mother. And so with all of these, we would be able to come to this conclusion. So we have enough information here to figure out that Marty and Leia are different animals, that they're both parents, that then Zia has exactly one parent, a zebra. We don't know which one, but we know that it must hold. And so forth. So these is assumptions. If we were to define these sorts of things here, we could actually automatically infer from these data that Zia is of type Zebroid. So it's an example we'll return to later. The interesting thing is that we can infer this without ever knowing which of the two is a zebra. So we don't know, we'll never know if Marty is a zebra or if Leah is a zebra. But we can still come to this conclusion here. So this is an example of more expressive forms of reasoning. So which of these are expressible in RDFS? So sire is a subproperty of parent, that's fine. Dam is a subproperty of parent, we can also express that in RDFS. A zebroid has exactly one parent as a zebra, that's not expressible. A zebroid has exactly one parent, a non-zebra equine, not expressible in RDFS. A zebra is a subclass of equine that we can express. An equine has exactly two parents that we cannot express. And two things cannot be related by sire and dam at the same time, we cannot express. So the ones we can express are just the subproperty and subclass relations. The rest we can express in now this extended standard that I'm going to speak about. So with OWL, we can say much more specific things, which is particularly useful. Well, there are some aspects of OWL that are generally usable, but these more specific types of definitions are useful in specific domains. So with this, we can start to reason about zebroids, but of course, that's not the only application. We can also reason about other complex forms of domain and about the world in general. So any questions? So in the next three classes, this class and the next two classes, we're going to speak about the web ontology language. And today I'm going to introduce the features of the language. In the following two classes, we're going to talk about more conceptual issues about expressive forms of reasoning, knowledge representation, and the limits of knowledge representation in terms of reasoning. So at some point, we'll reach the point that we can define so many things that we can actually define open problems, for example, in computer science, or we can express the halting problem, which means that the halting problem being undecidable, we can't write programs to solve it. So it'll mean that we can't have programs that can provide full reasoning. But for today, We're going to talk about the Web Ontology language, which has two versions. The second version was published in 2012. It's also a W3C standard, and it extends the RDFS standard that we spoke about in the last class. So it's quite a complex standard, and it has some formal underpinnings with respect to description logics, and which is sort of like a first order logic, a fragment or subset of first order logic that's designed to be decidable to allow for reasoning algorithms. So I'm not going to speak too much about this table. We'll use some symbols later, but I'll explain them as we go. So there is a sort of a logical underpinning for OWL. For today, I'm not going to talk so much about the description logics, but rather going to introduce the various features that OWL has with a running example based on this family, I guess, infamous family. Anybody know what the family is?
The Corleone family?
Yep, Corleone, the Godfather, from the Godfather movie, so the Corleone family. Okay, so we have some ancestor tree. So we'll see some running examples with family relations effectively. So first of all, before we see the examples, we have to mention two important logical assumptions, or lack of assumptions, some might say, for OWL. So the first is that is a logical assumption, or better to say a lack of assumption, which is called the open world assumption. So we have the open world assumption, which essentially helps us to answer questions like this. So we have an RDF graph here that has three triples. Vito has child Connie, Vito has child Sunny, Vito has child Michael. Okay, so here we see your three triples. How many children does Vito have according to this RDF graph? So it would seem three, right? So we could definitely say that Vito has three, has three nodes connected to it, right? So somehow in the graph, the node for Vito has three nodes connected to it for has child. But if we say three, we're assuming two things. The first thing is that the data are complete, which means that Vito could possibly have more children that we just haven't got in our data, that we haven't expressed in our data. So OWL assumes something called the open world assumption. So Vito has three children as one possibility, but actually what OWL considers is that, okay, maybe there's some other children that we haven't been given in the data. So unless we can prove otherwise, we're always going to consider that Vito could have more children and that the data are incomplete, right? It's not going to assume that the data are complete effectively. So here it would seem maybe that we could say that Vito has at least three children, right? Okay, the open world assumption, both RDFS and OWL take an open world assumption where anything that is not known is not assumed to be false. It's simply unknown. So the fact that we don't have more children here for Vito does not necessarily imply that Vito does not have more children, right? So in other logics and other settings, it's sometimes the closed world assumption is applied, where if we do not know something or we cannot prove it, then we assume it to be false because we assume our data to be complete. So if we have a data set about Nobel Prize winners, for example, and we ask, is Justin Bieber a Nobel Prize winner? We could, with the closed world assumption, say no, because we have a list of all the Nobel Prize winners and Justin is not there, unfortunately. So in this case, in OWL, what we're going to say is we don't know. He could be, because our data might be incomplete. Right? So without further information, Vito may have children that we don't know about. Okay, so why might this assumption be important for the web? To briefly answer, it's because essentially if we try to assume that web data are complete, it seems like a bad idea, right? Maybe we could define some parts of web data to be complete. For example, we might have a really up-to-date site of Nobel Prize winners, and we could say, hey, oh, you know, this data set here is complete. That's sort of a local closed world assumption. And there's some work in that direction, but in general, the most general setting here for RDFS NL is to take the open world assumption. And this has some implications for what we can infer or entail from certain OWL or RDFS definitions. So this is the first thing. The second thing is that in OWL, we have no unique name assumption. So returning to this here, we had sort of guessed that maybe we could say that Vito has at least 3 children. However, we can't even say that much because it is possible in RDFS and OWL that these are all names for the same child, that somehow we've named the same child with 4 different nodes or 4 different names. So we can clearly and intuitively see that that's not the case here, but it would be a very strong assumption to assume that we have 1 node for each entity or 1 name for each entity, especially on the web, right? It would be a very strong assumption. So in OWL, we don't assume that these names are unique. We assume that these names, or we rather consider that these names could refer to the same entity. So this gives us the answer that Vito has at least 1 child. And okay, unless we can prove otherwise. So maybe later we'll see some examples of how we might prove otherwise. So RDFS and OWL do not take a unique name assumption. 2 or more IRIs may refer to the same thing, or even literals and so forth. So we might have multiple ways of referring to the same thing. And without further information, the nodes that we have in our graph, essentially, multiple of them could refer to the same thing. For example, to a single person that is Vito's child. So why might this assumption be important for the web? If we were to think about, you know, the web and having to name things in a very consistent manner, it would again seem to be a bad idea. So we would have to enforce that the entire web agrees on the IRI to refer to, for example, Santiago, and that no location on the web can use a different IRI to refer to the same city, right? So this would be very inflexible and very much against the decentralized nature of the web, right? Sort of enforcing people to use some strict naming scheme it does not seem to be a good idea. So we have these 2 important assumptions or lack of assumptions for RDFS and OWL. Okay, with that in mind, and we'll see the effects of this later again, but any questions or doubts? It seems my connection is working okay on mobile, so that's good. Okay, so let's start with some RDFS. Okay, so we'll return to our examples. So this is the general format. So OWL extends RDFS, so it also includes the stuff we saw in the main features of RDFS that we saw in the last class. So if we have Vito, husband of Carmela, which is this triple here, we say as well that husband of is subproperty of spouse, then we could infer in this case, Vito is spouse Carmela, okay? So we already saw subproperty of in the previous example. On the other hand, if we say Carmela, wife of Vito, and wife of subproperty of spouse, then we can infer in the other direction, Carmela, spouse Vito, right? So we see these inferred triples are dashed here based on the subproperty definitions that we provided. So if we say that Mary is of type woman, in this case, subclass of, and we say woman is a subclass of person, then we can infer that Mary is of type person. Okay. So we've seen subclass in the previous class as well. Domain, if we say Carmela, mother of Fredo, and we say mother of domain female, then we can infer that Carmela is of type female, for example. We don't know that it's woman, we don't know that it's human, but we know female in this case based on domain. Range, Carmela has son Fredo, has son range male, and that implies that Fredo is of type male. So we have domain, range, and so forth, subclass and subproperty. So this is the general format I'll use for introducing the new features of OWL as well. If there's no questions. Okay, so the first feature that's very useful in OWL that we can use is equality. So we spoke before about that there's no unique name assumption. What happens if two nodes or two terms are really referring to the same thing? We can actually express this in OWL. We can express this using the same as relation. So what same as does, we could say that Vito old and Vito young. Okay, there's some arguments to be made that these are not really the same because they're, there's arguments against most of the definitions probably in this class, but there's arguments to be made here that these are not actually the same because they're two different characters played by two different actors and so forth. But okay, if we assume that we're really talking about the fictional person, we can say that these two are the same in some way. So if we say this, if we claim that Vito old is the same as Vito young, and what we can infer Vito young is the same as Vito old, okay? And also if we have some data about Vito old, for example, has grandson Vincent, and we have some data about Vito young, such as Mary, granddaughter of Vito young, what happens here? We can somehow combine the data for both of these nodes. So we have this sort of new combined entity that has the name Vito old or Vito young, and we have the data are somehow combined for that node because we know it's the same entity. So now we know that there's one entity Mary is the granddaughter of, and that has the grandson Vincent. So this is sort of to override the no unique name assumption, right? So in case there are two names that refer to the same thing, we use same as. On the other hand, we have the opposite, which is different from. So we can say that two nodes or several nodes really refer to different entities. This is especially useful for kind of nodes, it would be a lot to define this for every pair of nodes in the graph, because that would be quadratic, right? N squared. However, it's commonly used for example, Santiago de Chile is different from Santiago de Cuba, or the nodes that might be commonly mistaken. So if we have different from, let's say we say Connie is different from Sonny, Connie is different from Fredo, Connie is different from Michael, then the question is, what can we infer here? We can also infer Sonny is different from Connie, Fredo different from Connie, and Michael different from Connie in the other direction, okay? What's more interesting is that it changes somehow the answer to this question. How many children does Vito have according to this RDF graph? Anyone want to guess or to
at least two?
Yep, exactly, at least two. So this is because we know that there must be at least two different children. It's still possible that these three nodes here refer to the same entity, but we know that there must be at least two here, right? So this allows us to maybe then make more inferences later on. So now we know we can also in OWL, we'll see features later for counting things. So it would be in general, it's not so common to use different from explicitly. Often different from will be entailed or inferred from other definitions that we give. And we'll see examples of that later. So here we know that Vito has at least two children. Okay. So we have as well some notion of inconsistency in OWL, which is not really in RDFS. We can have some sort of syntactic inconsistency, some weird things, but there's no natural way of doing this. In OWL, we have inconsistency. It's a main feature of the language. So if we say, for example, Vito old is the same as Vito young and Vito old different from Vito young, then these are saying contradictory things that cannot hold together. So essentially what happens is that we're going to say that this entails false, which just means, hey, this is contradictory. There's a contradiction in the graph. According to the OWL semantics, this means that this graph is kind of nonsense, or it's not logically consistent. So here I'm going to denote that with this false symbol, or this false term. It means that really, well, the world is going to implode because it's inconsistent, right? So here's our first type of inconsistency that we can have. If we state same as and different from between the same pair of nodes, that leads to inconsistency. Any questions or doubts? Okay, so the first property axiom that we're going to see in OWL is pretty intuitive. Actually, most of the property axioms are fairly intuitive, although there's a lot of them to remember. But the first is equivalent property, which is essentially like a bidirectional subproperty of. So if we have Vito parent of Michael and Michael has child Mary, and we say later that parent of is equivalent to has child, which if we think about it for a little bit kind of makes sense. Parent of is equivalent property has child. Then we can infer that Vito has child Michael. But not only that, we can also infer that Michael, parent of Mary. Right? It's sort of like defining subproperty of in two directions, in both directions. So this is equivalent to saying parent of subproperty of has child and has child subproperty of parent of. Okay. So let me see what time it is. I think we're, so we can take a break for 10 minutes and we'll continue with the property axioms. Any questions or doubts so far? Okay. Oh no, that's the wrong one. My buttons. Okay. So the next feature of OWL that we can consider is inverse of. So, excuse me. So if we have, for example, that Carmela is parent of Sunny and Vincent is child of Sunny, we can see a clear relation between parent of and child of. They're the same relation, but they're just pointing in the opposite direction. It's like the direction is inverted. So we can define inverse of, which is sort of like, for example, parent of inverse of child of. It's sort of like the inverse of equivalent property, to say that two properties are the same, but just in different directions. And from this, we can infer that Sunny is parent of Michael and Sunny, child of Carmela. Okay, so we can infer in both directions using inverse of. So this is the inverse of definition. We can define a similar type of we can make a similar type of definition based on symmetric property, which is sort of saying a property is the inverse of itself, right? So sibling, inverse of sibling. Rather than write it like that, we'll say that it's a symmetric property like this, sibling type symmetric property. And what that tells us is if, for example, Connie is a sibling of Fredo, then we can infer that Fredo must be a sibling Connie. So it's something that holds in both directions. So if A sibling B, then B sibling A. So this is symmetric property. Transitive property, if we saw this example in the original slide, right? If A is part of B and B is part of C, then A is part of C. If Carmela is ancestor of Michael and Michael is ancestor of Mary, and we say that ancestor of is a transitive property, then we can infer that Carmela is an ancestor of Mary, right? So this allows us to capture transitivity of relations. So transitive property. Property chain axiom is again similar-ish to transitive property, with the difference being that the relations don't have to be the same. So neither the relations in the chain nor the relation that we infer. So the canonical example of that is if Sonny is brother of Michael and Michael is parent of Mary. What can we say between Sonny and Mary here intuitively?
That they are related?
Yep, but a more specific relation, right?
Que Sonny es el tío de Mari.
Yep, so Sonny, tío, uncle of Mary. Yeah. So what we can infer is how do we get this inference? To get this inference, we can define that uncle of is a property chain axiom, brother of, parent of. So this here is a list, and this defines an ordered list of elements, right, in turtle syntax. So it says that uncle of is sort of like brother of followed by parent of. So this allows us to create this connection here, this implicit this inference uncle of tío de. Okay, property chain axiom. So here there's a very subtle hint. I'm not going to draw too much attention to it, but this means features. If you see a 2 in the corner here, it means that this is a feature that's new to OWL2. Just to explain that. Okay. So we have a reflexive property, which is a slightly strange definition, but we can use it sometimes in conjunction with other definitions. It might make more sense. It's not so frequently used, I would say. But okay, what is a reflexive property? So we can say, for example, that similar to is a reflexive property, and it means that everything is similar to itself, right? So it doesn't matter if it's a person, if it's an event, if it's a book, if it's a movie, if it's a Boolean value, it basically everything becomes similar to itself. So we infer Connie similar to Connie, Freddie similar to Freddie, and all of the entities will be similar to themselves. Okay, another example, if we were defining the OWL vocabulary, using the OWL vocabulary, we could say OWL same as this type reflexive property, meaning that everything is the same as itself. So this means really that everything is similar to itself. Okay, any questions or doubts so far?
I have a question.
Sure.
So according to the well, what's shown in the PPT, we can use both RDF and OWL at the same time.
Yep, it's a good question. So these definitions that we have here, for example, similar to type OWL reflexive property, uncle of property chain axiom, we can express OWL in RDF. So we can represent these OWL definitions as RDF and represent them as a graph, and we can embed them in RDF graphs. So essentially, it's like OWL is a set of terms that we can use to define the semantics of RDF graphs. So we could, for example, copy and paste this into the RDF playground system that we've been using, and it will display it as a graph. It's just now that that graph has some special meaning, which means that, for example, from this RDF graph here with this OWL definition, we could infer Sonny, uncle of Mary. So it will allow us in a very similar way to RDFS to entail more stuff. In terms of the connection between OWL and RDFS, yeah, we can use RDFS in OWL as well. So OWL extends RDFS. There's some subtleties there in terms of certain things that OWL doesn't include, but these are very minor features. So we can also mix subclass, subproperty, domain range, property chain, axiom, symmetric property, inverse. We can use those as well.
Thank you.
Okay. And this is really a nice thing about OWL versus rules. Rules might be more intuitive in some cases, but in the case of OWL, what's nice is that the definitions we're doing are really RDF, right? So we can represent them as RDF and publish them alongside our RDF data. Okay, so functional property. So if we remember from databases, there's this notion of a functional dependency. And this is a similar notion here. So it means that something can only map to one value, right? Intuitively. So it's a function in a way. So Fredo here has biological father, Vito young and Vito old. So what can we infer from this? So what if we define, that has biological fathers of type functional property, it means that something can only have one value for has biological father. So intuitively, we might think firstly that, okay, this is inconsistent because there are two values here. We've stated that Fredo has two biological fathers, and here this is saying that Fredo can only have one. However, we have to recall the no unique name assumption, which means that actually rather than derive an inconsistency, since we don't know that these are different from each other, we can rather conclude that, hey, there must be then just one person with two names, right? So what do we mean by that? We mean that Vito old is the same as Vito young, and Vito young is the same as Vito old, right? So we infer that these are just two names for the same person. So we can infer same as in this way. As an aside, what if we said has father rather than has biological father was functional? So there are, for example, in the family, Tom Hagen is the adopted son of Vito, right? So in that case, maybe he has two fathers. He has his foster father, and he has his biological father. So in this case, it would seem, and one could argue maybe in the case of many of the definitions I've given that they don't hold, but in this case, it would seem not to be a good idea. Of course, as well, we could also have, for example, gay fathers and who have children. So that wouldn't be maybe so general. It would be too restrictive. So inverse functional property is the sort of inverse case of functional property, right? It does the same thing, just in the other direction. So now what it says is essentially, if we have two values, then they are, if two subjects, two entities have the same value, then they must be the same, right? So it's this case of Vito old has a biological father of Connie, and Vito young is the biological father of Connie. And then if we define a biological father of as of type inverse functional property, it means that if two entities have the same value for, two nodes have the same value for biological father of, they must refer to the same entity, right? So we infer here that these two must be the same, two names for the same entity, for the same person. Okay. So next we have has key. There's a lot going on here. So there's it's a slightly complex example, let's say, but the idea I think is intuitive. So we can say that two nodes or two entities, two nodes that have the same biological mother and have the same date of birth are the same, so long as they're not twins or triplets or quadruples or whatever it might be. So this is this class here, singleton, which is refers to a single birth rather than a multiple birth like twins or triplets and so forth. So if we have two nodes that are of type singleton and they have the same mother and they're born on the same date, we can infer that they're the same. So somehow has biological mother and born, the combination of both is like a primary key, or not a primary key, just a key for the class of singleton. It identifies the instances of singleton. So if we have Connie as singleton, has biological mother Carmela and born on this date, and Constanza singleton has biological mother Carmela and born on this date, the same date, we can infer from this that, okay, we have to define that singleton has key. This class has the key biological mother and born on the date. then we can infer that these two nodes refer to the same entity, right? So we can use this to find equivalences between nodes that refer to the same entity, and this can be quite useful. Irreflexive property basically is the negation of reflexive property. It states that something cannot have itself as a value, and it's probably more useful than reflexive property actually. So Fredo has brother Fredo, for example. If we define that has brother is type irreflexive property, something cannot have itself as a brother, then this leads to an inconsistency. This says, okay, this is inconsistent. One of these two triples here has to be incorrect. And okay, the world implodes. Asymmetric property is similar, but it's not just if something cannot have itself as a value, but rather if A has the value of that property B and B has the value of that property A, then this is inconsistent. So here we have Fredo has father Vito Young and Vito Young has father Fredo. If we say has father is of type asymmetric property, then we're going to arrive at an inconsistency, right? Somehow this cannot hold. So asymmetric property says that we can't have this sort of A has father B, B has father A pattern. Nearly there for property axioms. So we can also define two properties to be disjoint with each other. So what this means is essentially we can't have the same pair of nodes related with the two properties. So if we have Sonny has father Vito Young and Sonny has son Vito Young, and then we say has son property disjoint with has father, it means that again, okay, the world will implode, right? So there's an inconsistency here. So we're saying that essentially we can't have this sort of pattern with has son and has father. They can't relate the same pairs of nodes. And finally, we can also negate triples. We can say that a triple doesn't hold, which I'm using this very actually small in this case, negation symbol here to say not. Okay, so this says Fredo has not, does not have mother Connie, and Fredo has mother Connie. So this is obviously a very direct form of contradiction. So the way we represent negation in OWL is a bit ugly. And it's just because we have to represent the full triple and we have to negate it. So what we need to do is use an n-ary relation, right? So we need to use a blank node and then source individual Fredo, assertion property has mother target individual Connie. And we can also type this as a negative property assertion, but it's not necessary. So essentially this is the negation of a triple. So this is the negation of the triple. The Fredo has mother Connie. So it says this does not hold. And then we say that it does hold. So again, we cause the world to implode. We have an inconsistent world. Okay, so any questions or doubts? I know there's kind of a lot of features, but any questions or doubts about this? Hopefully in general, it's kind of more or less clear that, you know, these features are useful, right, for defining domains. And also it's useful to define the negations of things, right, or to define things that cannot hold, because that can ensure, you know, that we don't have nonsense or we don't have inconsistent statements in our data. It's better to be able to detect these inconsistencies, these problems in our data, rather than to leave them be or not be able to detect them. So false is kind of a useful feature. It allows us to know, hey, there's something wrong here in what we've defined. Something is inconsistent. Although on the web, it's maybe one can argue that it's natural to have inconsistent statements, but that's another matter. At least we can detect them when they exist. So okay, so we move to the last category of axioms and definitions we have in OWL, which are the class axioms and definitions. So the first thing we can do is rather straightforwardly, we can define, for example, two classes to be equivalent. For example, a human and person to be equivalent classes. So if we have Vincent is of type human and Mary is of type person, and we say human is equivalent class person, then we can infer that Vincent is of type person and Mary is of type human, right? So this is the same as saying human subclass of person, person subclass of human. It's like having subclass in both directions. It makes the two classes equivalent. So this is like an abbreviation for that. We can say that two classes are disjoint with, which means that essentially two classes cannot have any instances in common. So if we say Vincent is a mafia boss and we say Vincent is lawful, and okay, this seems a bit weird, right? So maybe later we define that mafia boss is disjoint with lawful. Someone cannot be a lawful, law-abiding person and a mafia boss at the same time. Then we infer an inconsistency. So the world implodes again. So we can say that two classes can never have an instance in common. What happens, just to give another example of how disjoint with can be useful. If we have Vincent is of type mafia boss and Mary is of type lawful, and then we define that mafia boss is disjoint with lawful, what can we infer between Vincent and Mary here?
That they are not the same?
Yep, precisely, yeah. We can infer that they're different from each other. They can't be the same, right? So this is what I meant earlier when I said that, okay, maybe we'll define different from in certain cases that are easily mixed up. But for the most part, these different from relations are actually going to be inferred from, for example, disjoint with definitions or from other types of definitions, where two things must be different, because if they were the same, it would lead to an inconsistency. So here we can entail that Vincent's different from Mary, and of course, Mary different from Vincent. Okay, so they're the two main types of class axioms, which are kind of defining relations between classes, semantic relations between classes. Another important thing we have in OWL is the ability to define classes based on other classes and properties. So here I'm going to use some symbols from this table, which I'm going to leave here for reference, but I'll just introduce the symbols as we go. So here, this is a symbol for subclass of, and this is a symbol for intersection of, much like sets, but we use the square one for classes, for description logics. So this states that mother is a subclass of a class that is the intersection of female and parent. So what we're doing here is defining a new class that's the intersection of two existing classes. So this is the class of resources, of instances, of individuals that are both female and parent. Okay, so what this effectively tells us, here we see the definition, mother subclass of, and this anonymous class, which is sort of like a blank note to represent this new definition. And this new class is the intersection of female and parent. This is how we would write it in Turtle syntax. So what this means is if we have Carmelas of type mother, anyone want to guess what we can say? What we can entail?
That she's a female and a parent?
Yep, precisely. Yeah, that she's of the types of these two things. So it's sort of like saying that mother is within the intersection of female and parent. So if we have something that's a mother, it must be within both of these classes. So this is intersection of. So if we can define intersection of, before that, let's take another example, but going in the other direction. This symbol here means equivalent class. So we saw subclass of before, but this means that it's sort of like a two-directional subclass of. So we could also go in the other direction, right? If we have here that these two classes are equivalent. So it means that mother is really the precise intersection of female and parent. So if we have Carmela is of type female and is of type parent here, what could we infer? We can infer now that this is sort of bidirectional. Now that it goes in both directions, we can infer that Carmela is of type mother. Okay, so if Carmela is parent and female, then she's of type mother. Okay, so if we can define intersection of, it seems intuitive that we could define union of. Union of is a bit more of a tricky beast when it comes to reasoning because it gives rise to multiple possibilities. So let's start with an example here, which is person is equivalent to criminal or lawful. So we're going to assume that, okay, animals can't, this sort of, dichotomy or this separation doesn't exist for animals. They can't really be criminals and they can't really be lawful, which I'm not sure is the case. But anyways, so a person is equivalent to the union of criminal and lawful. So we have defined it again in both directions, that these are somehow equivalent classes. So here's our definition here. If we say that Vincent is lawful, what can we infer?
He is a person.
Yeah, precisely, yeah. So we can entail that he must be a person, right? Because these things are equivalent. If we were to go about it the other direction, what could we infer?
He could be either a criminal or a lawful person.
Exactly, yeah. So now we don't know which, but we know that Vincent must be criminal or lawful. And this is kind of similar to the zebras that we, or zebra. I maybe mix the pronunciation. Zebra is Irish pronunciation, but zebra is more common. Zebra and horse in the zebroid example. So we don't know which is which. We don't know which is the zebra and which is the horse, or the equine parent. So in this case, yeah, we know Vincent is one of them, but we don't know which. So there's no real nice way to write that down. There are ways to write this down in RDF, right? We could say that Vincent is either criminal or lawful, but often what will happen is that, you know, based on this, although we can't really write something down, this might be useful information for us later. We might be able to figure out which one Vincent is, or we might be able to use that for other types of inference. So we have disjoint union of, which is also essentially very similar, but here there's an important thing, which is he could be both, potentially. He could be both criminal and lawful. If we wanted to rule out that case, we can use a disjoint union of, which says that really Vincent has to be one or the other, cannot be both at the same time. So we can use a disjoint union of, which rules out the both case effectively. It says that Vincent must be one of these options. And we can define a union of multiple classes, a disjoint union, where this basically gives multiple alternatives for what Vincent might be. Okay. So if we have union and intersection, then intuitively we could also consider the other aspect of set-based definitions, which is complement of, which is sort of like, if we remember set theory, it's everything that's not in the set, everything in the universe that's not in the set, right? So the complement of A is everything not in A. So we have to be a little bit careful here. So we really need to define a dichotomy, a separation of all things into two classes here. So what I'm going to say here is that dead is equivalent to the negation of not alive, and everything, no matter what it is, it's either dead or it's alive, effectively, is what this is saying. So this says dead is equivalent to the complement of alive. Okay. So if we know that Mary is alive, what can we infer? We could infer that she's not dead. Right. So here, this is really that she's alive. I'm not saying that she's of not alive. Sorry, this is Mary is of type alive, as written here. Then we can infer that the negation that she's not dead. And we use the negation in this ugly syntax that L has defined to say that something is not true. Okay. Spoiler alert for those who haven't seen The Godfather. Vito is dead. What can we infer from this? You've all seen The Godfather anyways, I'm sure, no? Hopefully. We can infer that Vito was not alive. So we can infer in both directions here based on this equivalence. Again, it works in both directions. So, okay, so one might ask the difference between disjoint with and complement of, because they're quite similar. Complement of is really what we would call a dichotomy. It's two classes that their union, the union of dead and alive in this case, defines the set of everything. Disjoint with doesn't do that. It just says that the intersections are empty of the two classes. So what does that mean? It means that there could be other things that are not, if we just said dead, disjoint with alive, then there could be sets of other things that are neither dead or alive. but complement really splits everything, the set of everything into two, into either dead or alive. So the last type of set definition we have is really to define a class to be a set of entities. So here we say that the Godfather is equivalent to the set of three entities, Vito, Michael, and Vincent, right? So we can actually define a class by defining all of its instance. We could also define all the regiones de Chile, for example, as really just enumerate them and say that this class is the class of regions of Chile. Chile is equivalent to this, or the US states or EU countries, whatever. So in this case, we say Godfather is equivalent to these this class of three entities. So if the Godfather is equivalent to one of these three entities. So what do we know from this? A little bit boring, but we know that Vito is of type Godfather, Michael is also of type Godfather, and Vincent's also of type Godfather. Slightly boring, but we can actually know more things. So there is another type of inference where if we know that someone is a Godfather, for example, Vito Young is a Godfather, then we know that Vito Young must be one of these, must be the same as one of these three entities here. Okay, so the second type of definition, let me see what time we have. Yeah, we can postpone that for the next, we can finish the class on Wednesday. So we're getting there. We have a couple of more different types of class definitions and we're done. Any doubts or questions? Okay, so if not in the lab on Wednesday, we're going to be looking at property axioms and we're going to divide OWL into various labs. So we'll have 3 labs on OWL. The first lab will be focused mainly on the property axioms, the transitive property, property chain axiom, the symmetric, and because there's quite a lot of features here to unpack, right? So we'll have 3 labs in total on OWL. So yeah, and there's maybe about 10 minutes more left for other ways of defining classes. So what's left are effectively ways of defining classes based on the properties and values that they have. So there's a number of ways for defining classes that way. Okay, so if there's no questions, we will see each other on Wednesday in the lab. Okay,